All right, so we're in section 4.2, going over compound events. So we have independent events in which the occurrence or non-occurrence of one event does not change the probability that the other will occur. For example, rolling a die or dice, tossing a coin or coins, drawing a card from a deck, putting it back in, reshuffling, and drawing another card. Independent events. Dependent events, the occurrence or non-occurrence of one event affects the probability that the other will occur. For example, drawing a card from a deck but not replacing it before drawing another card. The general multiplication rule for any events. The key word you're looking for in this situation is the word and. So the probability that A and B occur is the probability of A times the probability of B given is what the slash mark means that A occurred. That also equals the probability of B times the probability of A given that B occurred. This second part, this conditional probability given something, can be solved for to obtain the probability of A given B is the probability of A and B divided by the probability of B, or it could be the probability of B given that A occurred, which equals the probability of A and B over the probability of A. So what you're doing, if you look at these original probabilities up here that we first looked at, if you're solving for the probability of A, divide both sides of the equal sign by the probability, or excuse me, if you're searching for the probability of A given B, divide both sides of this equation by the probability of B. And if you're looking for the probability of B given A, divide both sides of this part of the equation by the probability of A, and you get this. When events are independent, the conditional part simplifies to either the probability of B or the probability of A, giving us for independent events, the probability of A and B is just the probability of A times the probability of B. There's none of the given that something occurred, okay, when they're independent. So for example, oh, and first, actually, let me backtrack a little bit. Take a look at example 4 on page 147. So on a roll of a fair die, what's the probability that you get a 5 on the die? That's 1 out of 6, right? There's 6 sides and one of them is 5. Suppose you roll 2 fair dice. What's the probability of 5 on the first die and 5 on the second die? So the probability of 5 on the first die and 5 on the second die is the probability of 5 on the first die times the probability of 5 on the second die. So each one of these is 1 over 6, right? 1 out of 6. So you have 1/6 times 1/6, which is 136. 136th, excuse me. This goes back to the idea that I talked about in 4.1 about using complements of an event. Suppose you roll 2 fair dice. What's the probability you don't get a 5 on the first die and a 5 on the second die? So that's going to be 1 minus the probability that you do get a 5 on the first die and a 5 on the second die, which is 1 minus 1 over 36, which is 35 over 36. So suppose there's a jar of 6 colored balls. an opaque jar. You can't see through it, right? You just put the balls in there. They're identical except in color. So there are 3 green balls, 2 blue balls, and 1 red ball. Compute the probability of drawing 2 green balls from the collection if the first ball is replaced before drawing the second ball. So the probability then of a green on first draw and a green on the second draw is the probability of a green on the first draw times the probability of green on the second draw. Remember, the first ball was replaced before you drew again, okay? So there's 3 green balls out of 6. So on the first draw, there's the probability it's green is 3 out of 6. You put the ball back in, you draw another ball, times this 3/6, which is 1/2 times 1/2, which is 1/4. So when events are dependent, the probability of A and B is going to equal the probability of A times probability of B given that A occurred, or the probability of B times the probability of A given that B occurred. Take a look at guided exercise 5 on page 150. And remember the previous example we just looked at, the first ball was replaced, right? This time it's not. Suppose there's a jar of 6 colored balls identical except in color. There are 3 green balls, 2 blue balls, and 1 red ball. Compute the probability of drawing 2 green balls from the collection if the first ball is not replaced before drawing the second ball. So in this case, the probability of green on the first draw and green on the second draw is the probability of green on the first draw times the probability of green on the second draw, given that you got a green on the first draw. So on the first draw, it's 3 out of 6. You got 3 balls that you are 3 greens that you've drawn from the 6 balls, right? But now you didn't replace one. So look at this denominator of this second thing over here, the second product. You have 5 in the denominator because now there's only 5 balls. And if you drew a green on the second ball, then there's only 2 green balls left. So this fraction becomes 2/5. So 3/6 times 2/5 is the same as 1 or equals 1/2 times 2/5, which is 1/5. Mutually exclusive events, or they're also called disjoint events, cannot occur together. So if events A and B are mutually exclusive, then the probability of A and B occurring equals 0. Here's an example. Suppose you roll a die. What's the probability that is both a 5 and a 6? Well, the probability you roll both a 5 and a 6 at the same time equals 0. Oh, let me just make sure. All right. The addition rule for events. Now, previously, we were looking at things that were, the keyword was and. Here you're looking for or, the word or. So see example 6 on page 152. The rule for this is the probability of A or B equals the probability of A plus the probability of B minus the probability that A and B occurred. The reason is there's overlap between these two probabilities, so that the probability of A and B is being counted, or the probability where they overlap is counted twice. So you're subtracting off the probability of A and B. So here's an example of something like that. What's the probability that it's a king or a diamond? Well, that's going to equal the probability of a king, which is 4/52, plus the probability of a diamond, which is 13 divided by 52. But this probability that it's both a king and a diamond has been counted twice. So you have to subtract the probability of king and diamond, which is 1 over 52. Combine these, you get 16 over 52, which reduces to 4/13. For disjoint events, the probability of both A and B occurring is 0. So we can simplify the addition rule and take off this probability of A and B so that the probability of A or B is just the probability of A plus the probability of B. Example, you draw a card from a standard 52 card deck. What is the probability that it is either a king or an ace? Well, in this case, the probability it's both a king and an ace is 0, right? So the probability of king or ace is just going to be the probability of a king, which is 4 over 52, plus the probability of ace, which is also 4 over 52. That's 8 over 52, which reduces to 2/13. Contingency tables. These are made as results of a survey that are partitioned into mutually exclusive sections and then used to calculate probabilities. Take a look at example 8 on page 155. So here's an example. A firm wants to test a new product in one randomly selected market area. So you have charts like this, and when you look at your exercises and the examples, you'll see that they come up with charts like this. This is on population density, okay? So it's divided going across the top here into urban, represented by the letter U, and rural, represented by the letter R. And so these are going down. Notice that if you add these two urban areas together, you get this row total, or excuse me, column total of 45. And if you add the two rurals together, you get a column total of 80. Notice that 45 plus 80 equals 125. Okay. Going across the rows, if you do 25 for East Urban and 25 for East Rural, they add up to 75. If you have 20 for West Urban and 30 for West Rural, they add up to 50. But notice these two also add up to 125. So you're going to be asked to find probabilities based on tables like this. Excuse me. So the probability of East, that's going to be the total of the East divided by the grand total of 125. 75 divided by 125 equals 3/5. The probability of urban, here you're going down. It's going to be the total urban, which is 45. Notice the numerator there, divided by the grand total 125, which gives you 9 over 25. And let me pause this just a second. All right, I wanted to reframe this so that you could see the entire problem, including the actual chart. So what's the probability that it's west and rural? So what you want to do is go up here where it's west and then go over to the right underneath the rural, and there's a total of 30. So that's 30 out of the 125. So 30 divided by 125 reduces to 6 divided by 25. What's the probability that it's east or urban? That's going to be the probability of east, which is the 75 over 125, plus the probability of urban, which is the 45 over 125, which you see right here, But then again, there's overlap there. So something's been counted twice. We have to subtract the probability. What are we subtracting? The probability that it's both east and urban, which is this 25 over 125, because it's been counted twice. And so that equals 19 over 25, 19 divided by 25. This bottom one here is the probability of urban given that it's east. Okay? So we restrict because we're given east, whatever you're given after this slash mark here, we're not looking at the total of 125 anymore. We're looking at the total of whatever you're given, which in our case, the total of the east is 75. So that becomes our denominator. So what about the probability of urban given east? That's going to be where they overlap. That's going to be this 25, except over 75 instead of 125, which reduces to 1/3. So take a look at page 157 for a summary of basic rules, that should say of probability, basic rules of probability. Look over look over the examples as you go through and guided exercises you see necessary. Take a look at these for homework. Number 3, 5, 7, 9, 21, 23, 25, and 29.